So today, kind of similar vein, we'll start looking at more by way of policy gradient methods, right, or actor-critic methods. So what we are going to look at today is a pair of approaches which we call DPG and DDPG, where DPG stands for deterministic policy gradient. In the area, what DDPG stands for?
Deep Deterministic Policy.
T. So typically the deterministic policy gradient setup, right? So is used with continuous actions. Now, what makes it challenging is, if you remember, in our stochastic policy gradient, we needed to have, the policy distribution, right? The action probability distribution, and then literally we were like trying out actions from there and taking the derivative of the policy probabilities, right? Now, if the policy probabilities now become deterministic functions, right? So basically, it's ones and zeros. Then the policy gradient theorem is no longer defined. Right? So we can't use the policy gradient update if my policy is deterministic. So we are going to look at how this has to change. So before we go there, just to make sure that you recap. So this is the policy gradient theorem. So we had a bunch of things in between one, right? So you have summation over A, Q pi is a gradient of pi, right? And summation over mu of s. And that's basically where mu of s is some kind of a distribution of the states under the policy that you are looking at. That can be taken as so this can be thought of as an expectation of this summation, right? And that is for discrete action. And when I want to do this for continuous action, so it basically becomes this double integral, right? And so this summation, so this is integral over S, so that's for continuous states, and integral over A for actions, right? And then I have my mu, right? And this is essentially the gradient of pi, right? And there's a slight notational change here. So this is basically how it's used in the DPG paper. And then Q pi SA. And here we are making it explicit by putting it as pi theta. And this can be taken as expectation, where the states are sampled according to mu pi and the actions are sampled according to pi theta. And you get this. In some sense, this also is now kind of moved off into an expectation. So this is the policy gradient theorem, the one that we know, right, for stochastic policies when you write it down for continuous states and actions. Right? So when you typically go to this continuous action spaces, these are in more complex control problems and robotics and things like that. It's possible for you to talk about continuous controllers, but to have them uniformly differentiable over all parts of it, right, could become a challenge. And even then, to do this for stochastic controllers, right, implement differentiable stochastic controllers can become even much more of a challenge. So what people typically end up doing is they implement deterministic controllers, right, with the differentiable control law. And the second thing is, when I want to take expectation over both states and actions, again, it's a problem. Here we have to take expectations over both states and action. That would really mean that I have to sample all possible actions, right? And that also becomes a challenge. So if you can reduce the expectation to only over states, which are sampled according to the distribution induced by the policy, right? And this greatly simplifies the gradient estimation. So in fact, with the DPG, in some sense, you can argue that the policy gradient computation becomes much simpler than it is with the stochastic policy. So let's do a little bit of a notation here. So the policy, earlier it was a mapping from states, actions to a probability. Now we'll just assume that it is deterministic policy. So pi of s is essentially the action that you have to take at state s. Right? And our performance objective now becomes something much simpler. Right now you only have an integral over s, right? Mu pi of s and q pi of s comma pi of s, right? And there is no need to do this integral over a because we have only one action that you will take for a policy pi. So is that clear? So now we can already see where things are going to be much simpler for us. And so the deterministic policy gradient. Right? So one way of looking at what we are doing with deterministic policy gradient, right, is to think of how you would do a normal update, right? So you would essentially let's go back to the previous slide. Right? So this is your performance objective, right? So when I want to do a update on theta, so what would I normally do is, assuming that my pi theta is differentiable, I'd like to take the derivative of q pi theta with respect to theta, right? So if I take the gradient of this whole thing, I like to take the gradient of q pi theta with respect to pi theta. And so what we do is essentially, so we kind of, sorry, with respect to theta here, we would like to take the derivative of q pi theta. What I want is this. Okay. What I really want to compute is this, and then I'll take a step in the direction of the gradient. Okay. So what I do is I use kind of a chain rule. And instead of taking the derivative of q with respect to theta, I take the derivative of q with respect to a and then pi with respect to theta. So that essentially gives me the overall the derivative that I wanted, right? And this derivative of pi is evaluated for at a equal to pi theta of s. So that's basically what I'm looking at. And now this this integral can be translated into this expectation. Now I can approximate this expectation by taking samples over states according to the policy pi. So basically I fix my parameters theta, take a lot of samples, right, compute this expression, right, take the mean and use that as the use that as my update. In fact, one way of thinking about it is we also avoided taking a max over action by moving in the direction of the gradient of q pi, right? So ideally, I mean, we should have just taken the derivative of this and actually, basically replaced it with the max possible action, right? If I'm doing policy improvement, right? If I've been doing a policy improvement step, so I have my pi. Think of what policy improvement would have been, right? So my new thing, right? So it would have been something like q pi of s comma pi. So I have some q function approximation. It's q of s comma max over a, right? And that would have been my policy iteration step, right? So I'll have to take whatever is my current pi, take the max action for that and set that as my new policy action for state S, and then estimate the value for that and keep doing this. That would have been my policy iteration, right? So doing this on a per state basis is some form of generalized policy iteration. And you can think of this deterministic policy gradient as doing even weaker form of generalized policy iteration, in the sense that instead of computing this max, which is hard to do for continuous actions, right? You compute the gradient of q pi with respect to the policy, right, and move in the direction of the gradient, right? So that's basically what we have done here. Does that make sense? The connection to generalized policy iteration. So, so how would I have done normally, right? Let's say I have a policy. I have a deterministic policy pi of s, right? And I would like to do policy iteration, right? So what would I do with that? So I'll first find my q, right? Q s comma pi of s or whatever. I've done that, right? And this would be my. Let me restart that. Okay. Let's do the policy iteration step, right? So what would I do with policy iteration? I'll start with some pi, right? In this case, we have pi theta, right? And then I'll do some evaluation of that, right? I'll do some evaluation of that. And then I'll be greedy with respect to whatever I have done the evaluation. So I'll basically get some pi theta prime, right? So to go from theta to, rather, from pi theta to pi theta prime, what should I have done is essentially after this evaluation, right? I should have picked the q that gave me the maximum action value in state S, right? Under the previous policy, right? So this is what I would have done here, right? So this is how my my policy improvement phase will be, right? So this is the evaluation, and then I do the improvement. So the improvement phase would essentially pick the greedy action with respect to the current value function q pi. Correct? Is that clear?
Yes, sir. Yeah.
Now what I'm saying is, hey, because this is a continuous action space, doing this max is a little tricky. So what I will do is I'll find the gradient, right, of q with respect to my actions, right? I'll find the gradient of q with respect to my actions, and I'll go a step in the gradient. So what am I doing here is that my new policy action, the value of the new policy action I'm taking, right, will be guaranteed to be higher than the value of the previous action I was taking.
Okay. So since actions are continuous, you cannot sweep through them because like you are doing with discrete actions. So you are taking the gradient to compute the maximum.
Yeah, I'm not even computing the max. That's a trick here, right? So max is the maximum possible improvement I could have done in the policy improvement step. But going any step in the direction of the gradient, right? Any step in the increasing direction of the gradient would give me a better policy. It's a even more weaker form of policy iteration. So max is the maximum possible improvement I can get from pi to pi prime.
Okay.
Right? But even any step in the direction of the gradient that improves the q function would be better than what I had earlier.
Okay. Okay, sir.
You get that?
Yes, sir. Yes, sir. Perfect.
And ironically, this was what my MS thesis was in IIC. How you replace the max over actions for continuous valued actions. I mean, I never did a version of DPG or anything, but this is something that we had worked out back then, and then had an actor network through which we kind of back propagate the gradients to get update direction for the critic. And it was back in '96, before neural networks fell out of fashion. Anyway, so get back. So what we are doing here is essentially taking this idea, right? So taking this idea of replacing the max to do generalized policy iteration to one of determining the gradient, right? In fact, I don't even need this, right? All I really need is a gradient of A of Q of S comma A, right? I can take that, and to achieve a step in the direction of the gradient, I basically will have to compute the gradient of the policy, right? Parameters with respect to theta, right? And evaluate that here, right? So this is basically a result of trying to approximate generalized policy iteration for continuous actions, right? And the nice fallout of it is that you lose the expectation over actions, and you just have the expectation over we just have the expectation over the stage. Okay. So this expression, right, is essentially a deterministic policy gradient theorem. So what is the one thing that it shares with the stochastic policy gradient theorem? So u pi of s, right, which technically depends on pi and therefore depends on theta, right? But that doesn't come within the gradient. So in fact, you don't have to take the derivative of mu pi with respect to theta. So this is something that we achieved in the stochastic policy gradient theorem, and we achieved the same thing in the deterministic policy gradient. So that's what makes it powerful in the sense that you could now do this expectation. And so also in the paper on the deterministic policy gradient paper, they show that for certain classes of stochastic policies, which are essentially like bump policies. Bump policies are policies in which there is a single action that is has the most probability, right? And then so eventually in the limit as stochasticity goes to 0, then there's a very natural way of defining a deterministic policy, right? So the bump will get the entire probability at the end of it, right? So bump means like this, right? And some kind of a distribution that does that. And there's a wide class of stochastic policies which you can characterize as bump policies. And so as the limit of this noise goes to 0, stochasticity goes to 0, this will now become a deterministic policy. And you can show that, hey, the stochastic policy gradient version for these kinds of bump policies will also kind of reduce to the same expression that we have here. And when in the limit of noise going to 0. Right, so that way it's nice in the sense that this is not something completely unrealistic. And so here are the set of equations. Of course, this is like an actor-critic, right? So we need the Q function. So we can look at it in the actor-critic setting, or you can and we can't get around. You can't really replace the Q function with the samples of the return or anything, because you really need the gradient of the Q with respect to the action. So it becomes trickier. So this is basically what we do, right? So you have the parameterized representation for the Q function. The parameters are given by W as earlier, and the parameters of the policy are given by theta. You get your delta, which is the TD error, right? And then you update the weights of the Q function using your regular TD update with the gradient of Q being taken with respect to W. Then when you come to theta, right, you update the theta, right, where the gradient of Q is taken with respect to A now, as opposed to taking the gradient with respect to W. And then you have the gradient of pi with respect to theta, but evaluated the whole thing evaluated at A equal to pi theta of S. Right, at SST. So that's basically the update rule for the deterministic policy gradient setup. So the DPG algorithm did not become super popular when it was proposed, primarily because it was a little hard to get to work with, and people are not really too enthused about spending that effort, right? Until obviously the deep version of it came along. But even then, so we have to, if you're talking about deterministic policies all the time, right? So we're actually behaving according to a deterministic policy. We know that that can be a problem, right? So it can get converged to something suboptimal. So we have to ensure some amount of exploration. So in the paper, what they argue is if the environment is stochastic enough, right, then the exploration is not an issue, because you will be moving to different parts of the state space, and therefore you will eventually end up taking different actions. Otherwise, what you do is you try to implement some kind of a stochastic behavior policy, so that ensures exploration, right? But then the policy for which you are estimating the value function, right, and the policy which you are updating happens to be a deterministic policy, right? The stochastic policy is like doesn't have all the nice properties that you want. It could be anything, differentiable. But at the end of the day, you use your important sampling updates to correct for the actor and the critic updates. Right, so that's basically off policy actor critic, right? And you can use important sampling for. We already talked about using important sampling earlier, right? In the policy gradient estimates, you can do something similar for both the actor and the critic. And just like in the last class on policy gradient or actor critic, we talked about compatible parameterization. You have a very similar condition on compatible parameterization between the W and the theta representations. Right? It's exactly the same condition. So the next thing we are going to talk about is Deep DPG. The idea behind DDPG is that it's going to combine DPG, but with ideas that we learned from DQN. So whenever we did DQ network, there are a few things that we looked at, right? So first thing is we use a replay buffer, right? And we use target networks, and some versions of DQN use batch normalization. And so batch normalization is essentially for every batch of samples that you take, you kind of normalize the input so that your network instability is minimized when training. So that's basically what happens with batch normalization. And of course, we are going to assume that the algorithm is off policy, and so you have your pi theta of S that implements the deterministic policy, and then you have some kind of a noise that corrupts that policy action, and that is applied to the work. So pi prime is essentially pi theta corrupted with noise. Okay. Now, so what we do is here are the update equations. So this is the critic network, right? So the critic, notice that here, right, the critic uses the target network parameters, right? So just like you use in DQN, right? So theta prime is the action suggested by the target network, and pi theta prime is action suggested by target network, and W prime is the parameters of the target network. And then you update the W just as you normally would do by following the gradient of Q with respect to W. And the policy network is updated by taking the gradient of pi theta st, which is the current estimate. So this is the current network. Well, this was the target network. This is the current network. And then the gradient of Q network respect to V. That's basically it for DDPG. Right. So putting all of these things together. So we start off with initializing the Q and the policy, and then we initialize the network parameters. Right. Then we get a replay buffer. So you select a noisy action. So you basically get the action suggested by pi t, add noise, and then you get the actual action that you perform, right? And then you put that actual observation you saw, right? ST, AT, RT, and ST plus 1, you put that in the replay buffer, right? And then a random mini batch of transition. So this is essentially where you are coming to like the Q function thing, and then you set your target, right, to be Q hat Si plus 1 pi theta prime Si plus 1 W prime, right? So let's unpack what this target is telling us now. So what is this target telling us? So essentially, these are transitions sampled according to whatever is the current behavior pi theta, right? And then it is corrupted by some noise. Right? But what would be the target here? It will be the action, right? it will be the action selected according to the current setting of the target network. And remember that that the parameters of the policy network are always being adjusted to follow the direction of the gradient. Right? So whatever was the value of theta at which point I selected this A. Remember, I'm sampling it from the replay buffer, right? So this A was selected from some old parameter setting for my theta. So compared to that old parameter setting for my theta, old setting for my theta, so this pi theta prime will be an improved policy because I have been following multiple steps of the gradient since then. Right? I mean, the farther back in the past it is, the greater the improvement I'm going to see when I'm looking at the target network. And now I actually do this estimate by taking an average over all the losses. Basically, this is like the TD loss, if you will, right? All the TD losses I compute, and then I then update the critic by minimizing this loss. That's a standard update. And then I can go back and update the actor, right? By not by looking at what the AI was originally, but looking at taking the gradient with respect to whatever is the action. I mean, taking the gradient of pi theta at whatever is the action that is specified by pi theta, and using and taking the derivative of the q pi and update it. And then we use a soft update or we're calling it Polyak averaging for the target network as opposed to doing a hard update for the target network. So the challenging part here is that, hey, if your target network is changing too slowly, right? If the target network is changing too slowly, then you might not be seeing much of an improvement, step to step in computing the target in this line. So that means essentially you have more hyperparameters to compute, right? So you have the critic update rule that you have. I mean, so you have some alpha W, then alpha theta, then you have tau. Right? You might have a tau W, the tau theta, if you will. Right? So all of these hyperparameters you have to tune. And so sometimes, DDPG becomes a little bit of challenging thing to get to work because you have too many parameters that you have to tune to get the exact updates that you are looking for. Okay. So did it make it clear? So how we are approximating the Q updates when we do this, even though we don't think about it, we are just using whatever is the latest estimate of the target parameters for the pi theta. It's actually approximating some version of the Q learning. Right. That makes sense. Yeah. Yeah. Go on.
Sir, how should the noise that we add to the deterministic action should be?
Well, it's an exploratory noise, right? So it could very well be some, I mean, depending on the nature of the problem, it could be a zero mean unit variance Gaussian that you could add to the action, right? Or if your action is multidimensional, it could be a suitably multidimensional zero mean Gaussian you're adding to it. Right. So typically it should be noise. And there shouldn't be an expected shift in the policy direction when you add the noise to it. Right? The noise should be such that when you take the expected value of AT should be equal to pi theta.
Okay.
I mean, if you are not actually, yeah, so then it's not really noise. Right? It's a systematic perturbation of the policy, and so you might want to take that into account to get better updates.